thanks for coming to this. Hi everyone, and thanks for coming to this theory seminar. We are very happy to have with us Archana Radhakrishnan from TIFR. Archana works in Lattice QCD. She got her PhD from William and Mary College, and now she's currently a postdoc at TIFR Mumbai. And her topic of research is hadron spectroscopy. And in hadron spectroscopy, this very interesting and recent recent area of research of tetraquarks and other exotic hybrid states. And today she's going to tell us about hunting a new kind of particle, the TBC tetraquarks. So, okay, most of the words are just about familiar to me and maybe not as familiar to the rest of the audience. So, Archana, over to you.
Thank you for the introduction. So I'll be talking about the TBC tetraquarks today. Before starting, I'll start with a brief introduction. So basically, we all know that the nucleus is made up of protons and neutrons, but then what we don't know really is that how the quarks and gluons, which are the fundamental particles of QCD, how they interact with each other to form the protons and neutrons, and also the rich nucleus, which is actually basically like a huge it's a soup of quarks, gluons interacting with each other to form these observable protons and neutrons in the vacuum. So it's very interesting to know this rich structure that QCD forms directly. So this is one of the motivations of studying QCD. Before moving forward, I'll explain a little bit more about like all the four fundamental forces and the elementary particles. So the standard model is the synthesis of the three of the four fundamental forces described by gauge theories. The coupling constant for each of those three forces. So for the strong force, the coupling constant is very close to 1 in dimensionless units. And for electromagnetic interactions, as we all know, it's 1/137. And the weak interactions is much weaker. And it's 10 raised to -5 GeV inverse squared. So if we see these, we see that the coupling constant with the strong interaction is the highest. But the thing is that the strong interaction is it's confined to a small region. So it's so that is why in longer distances we don't really need them as much. Whereas like in small nuclear scales, the strong interactions are one of the major forces coming into the picture. So the basic constituents of the strong force is we have the 6 quarks, and they interact through the medium, which is the gluons, similar to how the electromagnetic interactions they interact through photons, and the weak interactions interact through W or C bosons. Other than the hadrons, where the strong interaction plays a role, there are also the leptons. I won't be talking about the leptons in my talk after this, but then just a brief introduction. There's one important scale within the standard model, which is the mass of the quarks. So there are 6 quarks, and 3 of them, the U, D, and S, is what we call the light quarks because their mass is much smaller compared to the heavy ones, which is the C and B. The top is extremely heavy, and so we won't really, it's not usually considered in most of the lattice QCD calculations. A little more about the QCD. So the QCD is the theory of the strong force as we know it. So there are 6 quarks and 8 gluons, and they are mediated. So the gluons are the force carriers, and similar to how there is an electric charge for electrons, we have colors, which is the unit of force, if you can say, for quarks and gluons. So there are 2 parameters. One of them, as I mentioned, is the coupling constant, and the other one as well, which I mentioned, was the quark masses. And this, the QCD is a very beautiful theory, which can easily be written in this small Lagrangian. But solving it is the hard part, which we'll see how we do it in the other slides. Okay, there are 2 basic properties of the coupling constant of QCD that makes it.
Sorry, can I ask a question?
Yeah.
Sorry, Prasad, can I ask a question in between or?
No, it's fine. It's absolutely fine. No problem.
Yeah, hi, sorry, I'm not in this field. I'm a very, well, I have 2 naive questions. So one is, when you say, I mean, I know that people don't do lattice with top quarks, right? But
Mhm.
now there are hints of this in LHC, right? So I'm curious, do you know why people don't do lattice with top quarks?
Just because
Is there a political reason because that you cannot do it, or it's just a choice? I mean, you have 24 hours, you can't do everything. That's it. Is that what
I
is the
mean,
reason?
so it's not required because it's too heavy. So then the scales are, so what I'm talking about is mostly in the hadronic scale. So in that, the top quark physics can be easily decoupled.
Yeah, no, that's true. But the toponium is also a hadronic bound. I mean, it's a meson, it's TTBR bound state, right? So then, I mean, just a theoretical question. I know, I mean, it's probably not useful, but one can think just like you are doing light quark spectroscopy, or people do C and B, I mean, B spectroscopy. Can't there be anything called top spectroscopy? Sorry, this question may be completely random. I'm not in this field at all, so I'm just curious about it.
Maybe you're anticipating the you're anticipating the topic of this talk, because TUB is top quark tetraquark.
Oh, is it?
Maybe, but it was not. I mean, it was not directly relevant to QCD spectroscopy. That's why maybe nobody bothered to study the top quark on lattice up until now. Maybe that will change.
But there is no fundamental reason that you can't do it, right? That's my only question.
Yeah, I don't think there's a fundamental reason. I mean, there are challenges, but then there's no fundamental reason as to why you can't do it.
Okay. Okay. So one more thing, you say there are two scales. So you said there are two things, right? The mass of the quarks are being constant. And why don't you include the lambda QCD in this thing?
No, because like as inputs for so if I were to solve the QCD using for on lattice, so I don't need it as an input, right? I don't need lambda.
Okay.
Yeah.
Okay. Thank you. Okay, thank you.
Yeah, I think there's some issue with the screen share. I'm not able to let's see.
Oh, we can see the screen. We can see the screen.
Okay. Okay, good. Okay. Yeah. So basically, so what I was talking about was the coupling constant. So there's like one basic property of the coupling constant, how it runs with Q is what is very different in QCD compared to QED, where we see that at very low energy scales, the coupling constant is very high. So it cannot be solved. So in the hadronic scale, we can't solve QCD using perturbation theory, just because the value of the coupling constant is extremely high. And at very high scales, the coupling constant goes down. So then we can use standard perturbation theory at very high scales to solve QCD. At very low scales, an artifact of the fact that the coupling constant is very high is why we have confinement. People don't completely know the origin of it, but basically the idea is what happens is that because the coupling constant is so high that it is so if we imagine like a meson with one quark and antiquark, and if we try pulling it apart, the energy required to keep it
Can I ask a question?
Yeah, sure.
Yeah, why do you call it an artifact?
I call
It's not artificial in any sense, right? Confinement is very much a physical consequence.
Yes.
No, did you mean something else? Because
Yeah.
normally the word artifact is reserved for something that is artificial and can be gotten rid of.
Yeah, okay. So then I did not mean it to be artificial. Maybe it was just a choice of word. Yeah, it is physical. Like we can observe confinement. It is there in nature. I do not mean.
Okay, yeah, okay. Thanks for the clarification.
Yeah, no problem. Okay, so we can think of it as because if we try to pull together, like in a meson, if two quarks, the energy required to create a quark antiquark pair is much lower than that of having these individual quarks colored objects on its own. So this is why we can never observe a colored quark in nature. It always comes in confined as colorless objects called hadrons. So this is one of the reasons why it at hadronic scale it is very hard. It is impossible to use perturbation theory to solve QCD, and that is why we go for numerical techniques such as lattice QCD. So as I mentioned, the first point, one of the reasons that we go for lattice QCD is that the coupling constant is very large in the scales that we are interested in. And so we can no longer use perturbation theory. Another point which I would like to highlight is that the interactions within QCD, they play a very important role in the mass of these confined objects, hadrons. For example, in the case of mass of the proton, since we know that the proton is made of like 2 up and 1 down quark, but then if we actually, sorry? Is there a question?
No, I don't think so.
Okay. So we know that the proton is made of 2 up and 1 down quark. But then if we just simply, if we add the sum of 2 up and 1 down quark, we see that we don't even get more than 1% of the mass of the proton. In fact, 99% of the mass of the proton comes from the interactions within QCD. So in order to get even the precise mass of these hadrons, we have to take into account the interactions between the rich dynamics of the QCD. So that is why we have to resort to lattice QCD to even understand the simplest objects that we have in the nuclear scale. So now I'll explain a little bit about lattice QCD, since this is the tool that I use to study these to study these hadrons. So in lattice QCD, what we basically do is we discretize QCD on a 4-dimensional Euclidean lattice. So then we have two main assumptions. One of them is that we have a finite volume. The finite volume manifests itself as because now since we have a rigid we have something like a periodic boundary condition, so we have all the energy levels are discretized, but then we can use this as a tool to actually study the continuum physics. I'll explain how it's done in later slides. So even though we have a finite volume, we use it to our advantage as a tool. And the next thing is that we have a finite lattice spacing. So in general lattice QCD studies, what is done is that even though we have a finite lattice spacing, which is A, this is by lattice spacing, what I mean is that the grid size. And what we do is we study the same phenomena on multiple lattice spacing, and then we do a continuum limit, taking the lattice spacing to 0. And the other assumption for sure is that we studied on a Euclidean lattice and not, so what we do is we Wick rotate the time from Minkowski space to Euclidean space so that we can study this as Monte Carlo simulations. And in order to study masses of any of the hadrons, what we basically resort to is simple like path. So we can think of it as just like a path integral formalism. For example, like we know classically, if a particle is there in an initial state and a final state, we just have the straight line path. Whereas in quantum mechanics, all sorts of paths are possible, which is dictated by the Hamiltonian. So similar, and we know that in one-dimensional quantum mechanics also, we can use this path integral formalism by slicing the direction, and then we can study each of these individual elements as path integral to study the evolution of the object. So similarly, this can be seen as an analogy of what is done in QCD. Obviously, like the Hamiltonian in itself or the Lagrangian is much more complicated, but then this is the gist of what we are doing. So as I mentioned, we discretize QCD on a 4-dimensional Euclidean lattice with a finite volume and a finite lattice spacing, and we take into account these two assumptions. We try to use tools to remove these two assumptions, and then because it's on a Euclidean lattice now, so now we have we can use Monte Carlo sampling. So this is our function, and this is our integral. So the integral is actually weighted by this e raised to minus s action in Euclidean space, and then we get a number of Monte Carlo samples, and then we calculate. So so basically these functions that we calculate are mostly correlation functions, and I'll I'll explain for in the case of hadronic masses, we calculate 2-point correlation functions, in fact, to get the masses, which I'll explain a little later. So these calculations are not very trivial. It takes a lot of time and effort, and thanks to the community, there are like various standardized codes which people use for to get these what we call the gauge configurations. Since I'm talking about spectroscopy, I'll just brief just one slide about the experimental scenario. So there are multiple experiments, so including like BEST-3 in China, and then BEL-2 in Japan, LHCb and GluX in the LHCb in Europe, and then GluX in the US. So all these experiments are dedicated to study exotic particles that I'll be talking about, these tetraquarks, pentaquarks, and so on. So there's a rich experimental activity happening. So this kind of motivates even theory to have a complementary calculations so that they can be compared and we can see if QCD is working well in these regimes as well. Just as to show the success of Lattice QCD. So here I have this is taken from PDG. These points here are different Lattice QCD calculations for the mass of the ground state of these different particles, which are given in the x-axis, and these lines are the experimental values. We see that with just 2 inputs, as I mentioned, which was like the gauge coupling and the quark masses. These are the only 2 inputs that we have in these Lattice QCD calculations, and they're able to recreate like almost all the ground state values of the different particles very precisely, like especially like starting from the pion to rho and all these light baryons and mesons, as well as like even in the heavier sector. So the charm, the bottom. So these mesons as well. So we see that they are very much they match with each other, and this shows the success of Lattice QCD in studying these sort of ground state particles. So in the case of the tetraquarks, they are not the ground state. So there are some more challenges, which I'll say what it is in a little bit. But then this is like one of our calculations which we did in TIFR. So similarly, this is just the ground state of the. So there are there's a baryon with 3 charm quarks and spin 3½ plus. They combine spin 3½ plus and spin 3½ minus. So we've calculated the spectrum. So this red point is our recent calculation. These other, so below this horizontal line, they are the different Lattice QCD calculations, whereas above this, they are the different phenomenological calculations for the mass. So we see that the Lattice QCD calculations are slowly coming to conclusion that like they are more or less the value of this omega CCC is around this value, and ours is currently like one of the most precise calculations in both these sectors. So this also shows that how Lattice QCD can actually like study the systematics and get highly precise values for these hadrons. Now I'll switch gears a little bit and talk about these exotic particles. So we know that the commonly known hadrons are the baryons and the mesons. The mesons are made of just 2 quarks and 1 quark and an antiquark, and the baryons are made of 3 quarks. But then QCD doesn't restrict them to be just baryons and mesons, but they could also be there can be multiple quarks within a hadron. For example, there can be 4 quarks, which we call the tetraquark, or there can also be like 6 quarks in them, which we call the dibaryon. So in fact, even though mostly in nature we see mesons and baryons, these other particles which have like more than 2 or 3 quarks, they are not forbidden. But just for some reason, we have not seen a lot of them until recently. So this is the scenario right now. So on the x-axis, what I have is the date of the archive submission, and on the y-axis is the mass of the particles that have been seen by LHC. So there are at least 75 new hadrons that have been seen since the discovery of the Higgs in 2012. We see that out of these, at least 23 of them are exotic particles, with many of them these tetraquarks, which are made of like 4 quarks, and some of them pentaquarks, as I have talked about. So experimentally, since they are actually seeing all these particles, it becomes important that theoretically we understand why these particles were not seen earlier, and why it's and about like what their structure is, and things like that. So that is why we are interested by using lattice QCD techniques to study these same particles. I'll explain a little bit about how we study these within Lattice QCD. For this, I've taken an analogy from these Chladni figures. So what happens is, since we have now we are studying objects in a finite volume. So in this case, for example, like if we put powder on a vibrating object, we see that there are certain patterns formed which depend on the boundary condition. And then if we use the risk value method, it's just an eigenvalue problem to solve this. And then we get these irreducible representations. So similarly, since in the continuum we have these massive particles which have the JPC eigenvalues, but then since on a lattice we have a cubic symmetry, so then these irreducible representations are different because we have a finite volume, but then we can easily map them out from these irreducible representation of the lattice to the continuum irreducible representations. And another issue that comes with studying these tetraquarks and higher excited states is to study these amplitudes themselves. In the ground state, the study is a little more easier because because they are stable ground states. But then most of these tetraquarks and excited states, they are resonances. By resonances, what I mean is that they are very short-lived particles. So even in experiments, you don't see them in the final states. And
Excuse me. Yeah, I didn't quite understand your analogy with this vibrating sheet that you had maybe on maybe the previous slide. Yeah, what is the analogy that you have in mind that when you are what is the comparison of this to things that are done in Lattice QCD?
So what I basically wanted to point out was in the continuum, what we have is we have the JPC eigenvalues, right? These are the eigenvalues by which we can categorize particles. But then within lattice QCD, since we have a cubic symmetry, we don't have the spin parity. They are not good eigenvalues. So we have these irreducible representation of.
I can see that spin is not a good eigenvalue, but why is also parity not a good eigenvalue?
Because we have moving particles. So parity in the ground state, it's a good eigenvalue. But then since for excited states, what we need like moving particles. So then we'll have to use helicity. So parity is no longer, when in non-zero momentum, parity is no longer a good eigenvalue.
No, parity is a good symmetry of QCD, right? Parity x going to the space coordinate going to minus of itself is a good symmetry of QCD.
In zero momentum.
No, always. Parity is always a good symmetry of QCD.
So if you have like a moving particle,
if the particle is in motion, then it's not a useful symmetry. You need to give the particle a momentum to project to the excited state, not the ground state. But then it's probably not a useful symmetry for class.
These are, whether they are excited or not, you can always go to the particle exists. There is a rest frame of the particle because these are very massive particles, right? The bound states you're looking for. So in that rest frame, their parity is a well-defined symmetry. Is that not correct?
In the rest frame, yes.
Yes. And if you are predicting the mass of the particle, typically you discuss the mass only in the rest frame of the particle. Isn't that right?
Yeah, but these are so for resonances, we basically we don't discuss the mass as such. What we call it like is a pole position. So the idea is to look at the amplitude itself and then continue it in the complex plane and then get the pole and the width. So for excited states, that's what we look
Yeah,
at.
I mean, it is true. For example, you can do the same activity in QED, and you can look at resonances, and you can look at poles both in the on the first sheet or the second sheet. But parity is always a good symmetry in QED, and parity is a good symmetry in QCD too.
Yeah, in the rest.
Just because the particle is moving does not mean that you lose it as a symmetry.
Yeah, I mean, you don't lose it. I mean, you can always move it back to the rest frame.
No, it just means that there is another state in the system in which the particle, in which the particle is moving in the opposite direction. There is another state of the same energy in the system in which the particle is moving in the other direction. That's what it means, isn't it? I wouldn't say that as loss of parity, loss of that you lose the symmetry.
Yeah, I mean, yeah, you don't lose the symmetry because you can, I mean, as you said, like you can, in the rest frame, it's always a good symmetry.
And also, there is another state in the system in which the particle is moving in the opposite direction with exactly the same energy. So there is it is a good symmetry. If you so I don't know that I would describe this as losing parity as a symmetry. Rotations I understand because you work on a cubic lattice, whereas that is a much smaller symmetry than full rotation group. But I'm curious to know why you included also parity in your list as having been lost.
So basically, like when we have within the irreducible representations, when you have like a moving particle, what happens is parity mixes. So for the zero momentum particle, we can have an irreducible representation that is of a particular parity. But then whereas in the moving frames, what we have is we have like sum of different parities in these moving, like suppose if the momentum has one direction, like 1, 0, 0, where there's one unit in the x direction and 0 in the y and z directions, the opposite parities, they mix. So one irreducible representation can't be of a particular parity.
Okay, but like I said, if you do the parity transformation, then you find a particle with having the opposite momentum. So that should exist in the spectrum of your theory.
Yeah, I mean, I'll have to think a little bit more about that.
I would be very confused if you said that parity is not a good symmetry in QCD, which is what you are doing. You're doing
No,
only QCD, right? You're
yes.
not including weak interactions.
No, I'm not including
Yeah,
weak.
so I would find it very disturbing if you said that.
No, it is. It is a good symmetry in the rest frame. I'm just saying that within
In
the
all frame.
yeah,
It's not a
sorry.
question of rest frame. If
Yeah,
you're
okay.
moving, then you will find another state
Yeah.
with which is moving in the opposite direction with exactly the same energy and all the other quantum numbers being exactly the same.
Right.
That is what it means for parity to be a symmetry.
Yeah, but one thing which what I'm trying to convey is that within the irreducible representations, you can't each irreducible representation is not of a particular, like in the zero momentum, it is of a particular parity. But then whereas since we have objects in these irreducible representations, just by looking at the name of the irreducible representation, you can't say that it's of a particular spin or parity. You'll have to talk in terms of helicity.
Maybe we can maybe you can tell me later about this point. You can please continue.
Okay. So since most of these states are resonances, so I'll talk a little bit about like how resonances are being how we look at resonances. So basically there are three main properties of a scattering amplitude that we try to include in most of the amplitudes. That is, first of them is unitarity. So the imaginary part of the scattering amplitude is equal to negative of the phase space, which just comes from just comes from the fact that the total probability is conserved. So all the incoming particles should be equal to the total energy of the incoming particles should be equal to the that of the outgoing particles. And next is causality. So causality actually restricts the analytic properties of this amplitude, and so it has to. So it says that it should be analytic in the upper half of the sheet 1. So then you can only have poles, which correspond to these resonances, either on the real axis either below the threshold or off the real axis in the second sheet. And this is what we this is how we look for resonances. We look for the analytical properties of these amplitudes that we extract. This happens both in experiments and in lattice QCD. So all the energy, the spectrum that we have is always on the real axis, and then what we do is we analytically continue it to the complex energy plane, and then we look at the poles. We search for poles to find resonances, and then we get the mass and the width of these resonances, and this corresponds to the different bound states and resonances that we see. So now a little bit more about the tetraquarks themselves. So the tetraquarks were first seen using the bag model approach by Yaffe in 1977. But it was only after 2 decades that the first experimental observation was seen by the Bell experiment. They observed the X3872 in the pi j psi invariant mass. So on the y-axis here, we have the number of events, and then on the x-axis, the pi j psi mass. And then there's clearly like a bump around 3872, and this corresponds to the X3872. So this was the first experimental observation of any tetraquark. But then if we look at the heavy meson sector, especially the charmonium spectrum. On the right side, there's a plot of the charmonium spectrum in the different JPC eigenvalues. So what we see is that there are many ground states that are established, which are the of yellow, this yellow states that have been well established. But then there were many that were seen and not predicted by, they were seen in experiments, but then they were not predicted by any of the models. And then there were a few of them that were predicted, but then they were undiscovered. So then this sector just below, just above the 2MD mass, we see that there are many states that we still don't understand very clearly what their origins are. So we don't know if they're multi-quark resonances, hadronic molecules, or just kinematic effects. So we should understand them very clearly using theoretical tools in order to say something more about these states. So this is one of the main motivations of studying these particles. So we see, as we saw in the previous slide, there were many states seen after the X3872 by different experiments, and their possible quark contents were also put forward. And we see that one thing common in all these is that they are mostly found in the heavy quark sector. So most of them, they have like one. So in the first case, we have like one heavy quark, and then the second, the X3872, we have the CC bar heavy quark, and then so on. Another important sector which I'll be concentrating on in this talk is the is this sort of tetraquark, which has like 2 heavy quarks and then 2 anti-light quarks. So these are prime candidates for extremely long-lived particles, because phenomenologically you can think of it as like these 2 heavy quarks, they form like a core, whereas like these 2 anti-light quarks, they form like they bound separately together, and because of that, like there's a strong interaction between them, and they tend to be long-lived. And this was experimentally seen as well when
I have a question.
Mm-hmm.
If I remember correctly, Jaffe also talked about light tetraquarks.
Yes.
Made up. Do you know if any of the light tetraquarks have been discovered?
Not that I am aware of, but then there are some speculations that like some of the light ones could be like the F0, if I'm not wrong, like some of the resonances, they could be tetraquarks, but then nothing has been explicitly seen.
Okay.
Okay. So the TCC in 2022 it was discovered. So this had a CC and a D bar U bar. This was a quark content. It was seen by the LHCb, and as expected, it was just seen some few MeV a few keV below threshold. As expected, this was pretty long-lived. It was seen in the invariant mass of the DD pi. As we see that here in this plot, there is a bump corresponding to the TCC. So since TCC has been discovered, there are many questions that arise. What does the theory tell us about these particles? And then where should experiments look for more of these sort of tetraquarks? And obviously, like the other possible, instead of two C's here, if we could have the other heavy quarks that are possible, would be either two B's or a B and a C. And I'll talk about these, the theoretical and the experimental scenario in both of these. So before moving forward, this is a slightly.
Can I ask a question here? Hello?
Sorry. Yes.
So can I ask a question here?
Mm-hmm.
So in the previous slide,
Mm-hmm.
so earlier you talked about X3872, right? So I know that there are some people think that the X3872 is a near threshold bound state of D0, D0 bar, D0 bar star meson. So what about this TCC plus? Can these be any these molecules, or are we guaranteed that these are 4-quark bound states?
Okay. So basically, like within, at least theoretically within Lattice QCD, they have not confirmed if it is. There are some speculations depending on the what you need to know is the radius, and the radius has not been calculated yet. And so I wouldn't say there is a concern.
I know experimentally people talk about that the way to distinguish the near threshold resonance versus the for the X3872 to distinguish its properties, to measure the line shape very precisely, and then the line shape will tell you whether it's a near threshold resonance or it's a bound state of 4 quarks or whatever, right? So does that same argument go through for this TCC plus also?
I mean, there are certainly like such arguments for TCC as well, and but I think these arguments are not as rigorous. What the plan is to do is if there's like an external probe to look at like some sort of like a 3-point function where like you have an external current looking at the size of these particles, that's where like you can say for sure what these are.
So if this TCC plus is a molecular bound state, what are these constituents? Do you know? Which is probably not what you're working on. Just curious.
If it is a molecular bound state, so I mean, if it is a molecular bound state, then it would probably just be like it would just be like a DD star.
Okay. Thanks. Thank you.
Okay.
Yeah, maybe I have a related question. I mean, is there a distinction between a molecular bound state and something that is a 4-quark bound state, which is not cannot be thought of as the weak bound state of two mesons? Is there such a distinction, or are all tetraquarks thought of as bound states of two mesons?
When you look at the pole itself, like this doesn't distinguish between molecular or tightly bound. But then if you look at the radius or the size of these, then you can actually distinguish if they are loosely bound loosely bound to mesons, or if they are tightly bound for quarks.
So would that not be a conceptual difference between these two types of tetraquark states?
I think it's a difficult question actually.
I would just like to know what she thinks about it.
Sorry.
Yeah, I mean, I was asking whether there is a conceptual difference between a 4-quark bound state, which is not a bound state of two mesons.
Can I say something here?
Yeah, of
Uh,
course.
So just because, I mean, if it's a bound state of two mesons, its mass has to be in the right ballpark, right? So in some sense, I don't know the answer, I'm just guessing. I mean, at least for the X3872, it turns out that the mass is close to the uh, masses of these two D0, D0 star.
No.
Hmm.
Yeah.
So this may not be true. I mean, if you look at the spectrum, this may not be true for all of them, right? So that can be an easy. I don't know what is the real answer. I'm just guessing.
I mean, that is one of the parameters where if you get the bound state very close to the threshold, there is more of a chance that it's weakly
Right.
bound. So then it can just be a molecular state. Whereas, like if it's much below, then you know for sure that it is tightly bound.
Yeah. Yeah.
So it looks like conceptually there is some difference between these two types of tetraquarks. If you can find the second type of tetraquarks.
But
You can't think of it as two mesons that are just hanging around next to each other and are weakly bound.
like by these tetraquarks, you're saying, but it's like what what he said is yeah, if it is very highly like deeply bound, then there's more of a chance that it is just four quarks very close to each other compared to another thing, which at least like within lattice calculations, since we have operators in each of these different when I show the calculation a little more deeply, we actually have different operators. So some of the operators that we include are just meson operators, whereas like some of the operators that we include are these four
Genuine four quark operators and two meson operators, right?
and we could I mean, this is not a very rigorous way, but then we could look at the weight that each operator gives to the ground state, and with that we can actually say something about which operator contributes more. So depending on which operator contributes more, you could probably say, okay, this is more likely to be just four quarks tightly bound together, or just two different mesons just like
So do you have examples of situations where you can
Maybe Sachin, maybe a little after the talk, maybe.
Okay.
It's because I think this is before actually the actual topic of the talk, probably, right?
yeah.
We can discuss it after the.
I don't know that there is a time limit, is there? Okay, we can come back to this at the end.
We'll come back. I mean, we can stay online. That's not a problem. But for the rest of the audience also, maybe after the talk we can discuss it, and then we can stay online afterwards. That's okay.
Okay.
Oh, okay. So basically, we can look for other possible states which are similar to the TCC, which would be either the BB with the two light quarks, or the BC with the two light quarks. So this is just an overview of it's slightly outdated of the current scenario, both experimentally and within Lattice QCD. What states have been seen. I'll start one by one explaining like some of these states, and then I'll go to this R calculation. So before moving forward, I'll just briefly explain what the methodology is within Lattice QCD, how we calculate these masses. So what we look at is the time dependence of two-point correlation function. By looking at the time dependence of the two-point correlation function, we are able to extract the energy levels that are discrete. And then this time dependence, we fit the time dependence, and then we get these energy levels for each of these irreducible representations that I talked about. And then from there, what we do is we map these discrete energy levels to the scattering amplitudes using a method called Lucius method, which I'll explain in the next slide. And then after that, what we do is the lattice spacing dependence. So we have to remove that, and then another assumption that is done in lattice is that we don't go for so the physical pion masses, they are much more computationally intensive. So then the pion masses that we use are slightly higher. So we do a chiral and continuum extrapolation to get the physical value of the binding energy and so forth. In this slide, I'll just explain very briefly about the finite volume scattering. I'll explain it using just one-dimensional quantum mechanics. So if we have a wave function going to a finite potential, what we know that once the wave function goes in, what comes outside, we have a phase shift. And this phase shift is because of the interaction of the wave function with the potential. But then now if we put the same well inside a periodic boundary condition with minus L/2 to L/2, we'll have to, there are constraints at the boundary, and by solving these constraints, we see that the energy levels, they are discretized, but then these discrete energy levels, they are related to the phase shifts using this formula. So something similar happens in lattice QCD as well, where the discrete energy levels that we get for each of the irreducible representations, they are related to the phase shift, and this relation is from Lucius condition, and this is what the condition looks like, where these are the Lucius zeta functions, which are known functions, and so we can easily map from these discrete energy states to the infinite volume phase shifts. So this is like a cartoon picture of what is done. So in experiments, as we know, we have we can scan energies above threshold, and then we get the phase shift. Whereas in lattice QCD, what we have is we have discrete energy levels, and then we are able to map these discrete energy levels to a particular phase shift, and then we can fit these phase shifts to get what the phase shift kind of looks like. And we can also write the Lucius condition in this form, where F inverse plus M, where M is such infinite volume scattering amplitude, F inverse is a known function, and the determinant of this is equal to 0. So we basically solve this, and then we get our scattering amplitudes and phase shifts. Okay. As I mentioned earlier, the other possibility, since the TCC is already found, is the other possibility is the TBB and the TBBS, which has the quark content as BBUD and BBUS, and the spin, the spin parity quantum numbers are also given. And we see that there are multiple calculations in lattice QCD for these different states, and most of these lattice QCD calculations they are more or less, they show that these are deeply bound both in the BBUD as well as the BBUS channels. It's slightly more bound in the BBUD, close to like minus 100 MeV. And there's a clear consensus on these states, but then these states, since they are like slightly heavy, current experiments may not be in the energy range to look for these particles. And so then we look at the others, which is the TCC. So since the TCC has already been seen, but then we see that within lattice QCD, there had been calculations even before it was seen. So this is one such calculation by the group in TIFR. In 2019, so they had looked for the TCC and they had found it. So at a different, at a higher pion mass, and there were other calculations as well that saw similar lattice QCD calculations that had seen TCC similarly before the experimental evidence. But there were some limitations in these calculations because these calculations, as I mentioned, like these finite volume effects are important in this case, and these calculations do not take into account those finite volume effects. Whereas since the discovery, there has been many other calculations. For example, this was like done by Padmanathan IMSC, where the finite volume effects were also taken into account, and they've calculated the value of the binding of the TCC, and right now, this is these are all the different calculations that have been done, and more or less they all agree on the fact that there is a TCC present. And the binding is so even though there's a little bit of scatter in the binding because of the various different pion masses and some artifacts, systematic errors not taken into account, more or less they say that there's a shallow bound TCC in these channels. That is what QCD tells us. The case of TBC using lattice QCD is a little more dicey because there are only initially there were only, currently there's been one more calculation which I'll talk about as well along with us. But then earlier there had been only two calculations, and then both these calculations they could not really say for sure if there was a TCC or not, because in one case they actually their statistical errors were high, and so they couldn't they said that they don't have a conclusive evidence if there's a bound state, and in the other one the finite volume effects were not taken into account. So this is another thing that motivated us to do this calculation. And so since the TBC can be found in both the 1 plus and the 0 plus JP eigenvalues, so in both the cases, the scenario was the same. So yeah, so this is what we did. So these are all the lattices that we use. So what we use are these ensembles that are calculated by the collaboration called MILK. So the type of discretization that they use is this what called staggered quarks, His action. So all the valence quark that we use, they were implemented. So these are just like lattice jargon where the valence quarks were implemented using this particular action, whereas the bottom, in the case of bottom, we use non-relativistic action, but then for the others, for the other quarks, they're all relativistic action. So we calculate, we have actually 4 different lattice spacings so that we can do a continuum extrapolation, and then we have 5 different pion masses, so that we can do a precise chiral extrapolation, and we calculate the V star D scattering where the TBC bound state is supposed to be seen, and we on all these lattices to get the value. Okay. So we calculate, as I mentioned, we calculate 2-point functions on the lattice to look for the ground state energies. This is a brief example of how it is done. So we have different operators. In our case, we use 3 different operators. So we use so this is like meson like operator, as I mentioned, and then this is something which is diquark anti-diquark kind of operator. So this operator would be more like a tightly bound tetraquark kind of, this would give that scenario, whereas these 2 operators would give a scenario where there's just 2 mesons like weakly bound. And what we do is we calculate the 2-point correlation functions for each of these operators, and then we get a matrix of correlation functions. And once we get a matrix of correlation functions, what we do is we solve this eigenvalue problem, which is called the generalized eigenvalue problem, in order to get the perfect linear combination of these operators that project the ground state well. So we solve this, and then we get this sort of a linear combination of these different operators, and then that project to the ground state. And using this, we actually calculate the ground state energies in each of these channels. For example, since this exponential dependence is what is fitted, and in order to view this a little more clearly, what we plot here is the effective mass, which is the log of the correlation function at time t divided by t plus 1. So if we take this ratio, we only get this energy. So we see that there is there's a lot of noise initially, and then slowly it starts plateauing, and then the plateau is the part where we get the energy, and then we fit that. So we fit it in 2 different ways. One of them is, this is just the ratio of the value of the correlation function with respect to the value at the threshold. So this deviation here just gives us the binding. That is the difference between the threshold and the ground state in this channel. Whereas on the right side, what I've plotted is just the on top is we have the threshold, and below is the ground state energy that we get in this channel. We see that in both these methods, more or less, the value is similar. We get around 0.02 net binding in lattice units. Using these 2-point correlation functions, we look at the ground state energies of the bcud, both in the 0 plus and the 1 plus channel. So on top, I have the 0 plus channel, 1 plus channel, and below I have the 0 plus channel. So across, as I mentioned, we have like we have 5 different pion masses, and we have 4 different lattice spacings and volumes. And one thing that we see across all these calculations is that like in every pion mass and volume, we see that the ground state is much below the threshold. So this already gives us an indication that there is a bound state present. But then we also have to take into account the finite volume corrections in order to be sure of, in order to get the continuum amplitude and be sure of what is happening here. So that is what we do. This is an example of one of the, in the case of the 1 plus, the axis 1 plus channel, what we do is, so this is the k cotangent delta, which is almost equal to 1 over the scattering length. So I plot on the y-axis the k cotangent delta, where delta is a phase shift normalized by the threshold energies, and on the y-axis is the k square. And what we see is there is this we plot the values, and then this is the bound state constraint. By bound state constraint, what I mean is if there is a pole in the scattering amplitude, if we think of a simple Bright-Wigner form, we see that the k square is equal to this k. So then because of that, like we have this this curve that forms bound state constraint. And since the values cross through this bound state constraint, that means that there is a pole in the amplitude. But then there is also non-trivial lattice spacing dependence as well, as we see, because these curves that we see, individual curves, they're not like they're not very continuous. So we take that into account, and what we do is we do a chiral continuum extrapolation, and we get that for both these channels. So our final result is that there is a binding. There a binding of minus 43 MeV in the case of this. In the case of the scalar channel, and then in case of the axial vector channel, we have the minus 42 MeV. So our finding suggests that there is the binding energy decreases with increasing light quark mass, and this indicates the presence of a real bound state at the physical quark mass, which we have extrapolated to, and so there is an attractive interaction in both these channels and the presence of a bound state. So as I mentioned, like as we were doing our calculation, there was another calculation also which found a similar bound state in these 2 channels as well using lattice. So here, similarly, I have like a compilation of all the results. About the horizontal line are the different phenomenological results of the binding energy of bcud in the scalar case, and on the right is the axial vector case. And then we see that in lattice QCD calculations, both of them, they say that there is a bound state, but then the binding itself is different. So these could be because of the chiral continuum extrapolation was not done in this other calculation, whereas in our calculation we use some operators, but then we could always use like even more operators in order to get so this just shows that there are more improvements to be done in these calculations in order to clearly say what is going on here. But then one thing is for sure is that there is a bound state present. And another thing that would be interesting to see with these something in future would be after looking at these the binding and the presence of a bound state in these channels would be to see the radiative decay of these channels. And this was in lattice QCD there are methodologies that we can use to calculate these as well with recent progress. Something like this we could calculate, and we could look at the radiative decay of the TBC, and with that we could say about like the size and the and some like if they are molecular bound states or deeply bound tetraquarks, we could say something about that by looking at these radiative decays. And with this, I'll like to stop, and if there are any questions, I'll be happy to take them. Thank you.
Hi, Archana. Thank you very much for this nice talk. We can take some questions now. Uh,
Yeah, I just want to ask, I have lots of questions, so is there a time limit?
no. I mean, unless I mean, yeah. If unless Archana has a constraint, I think it should be okay. Yeah.
No, it's fine.
Yeah, so there are several things that you said that I need to understand more. At near about slide 26, you talked about time dependence.
Mm,
Uh,
26. This one.
yeah, see, you said time dependence. So now, the question I had is that you started off your talk by saying that you're looking at Wick rotation and
Mm,
you're doing Wick rotated.
mhm.
The theory that you're studying is the Wick rotated theory.
Right.
So, how do you extract scattering information from a Wick rotated theory?
Yeah, so that is where like the Lucius formalism comes into account. So what so
So,
we
can
have
you explain what Lucius formalism is, at least
yeah, so I mean
approximate?
yeah, approximately this is what we are doing. So, so we have so this time dependence. So maybe I'll first explain what I mean by this time dependence. So this
Yeah.
time dependence just comes from this operator here. So basically, so I have an operator creating an object at time 0 and then annihilating it at a different time t.
Yeah,
So
but this time that you're talking about is Euclidean time, is it?
Euclidean time, yes.
Okay. Okay. So that's not the same as real time.
Yeah, no, it's not. It's just yeah, it's not the same as the real time.
Okay. Yeah. Sorry. Please go on. You were explaining what is Lucius method.
Yeah, so basically with this, so I have an operator this and an operator annihilating, and with this, what I calculate the correlation function as with respect to time. So this is what I've plotted here, like a correlation function of this. For example, if it's just one operator, then correlation function of this operator as a function of time. And since we know that this correlation function is supposed to decay off with respect to this energy, because of the time evolution. So we kind of fit this function and get these energies. Uh, and but then the issue with these energies is that these are finite volume energies and these are discrete values, instead of like how you have in experiments where you have a continuous you can actually sample at any given energy level. So now what I have is in each irreducible representation, I just have some discrete energy values. So this is what I get from lattice calculations. And now what I have to do is I have to map this to the continuum to continuum scattering amplitudes. And for this is what we use Lucius method. Basically, Lucius method, what it does is it takes the so if you have a periodic lattice, it takes the properties of the periodic lattice and is able to say that okay, if as a function of energy, so these discrete the momentum of these discrete energies, they can be related to some amplitude that we parameterize and.
So in that formula that you showed, determinant of F inverse plus M,
Mhm.
what is F and what is M?
So F inverse is like a known function, which is it comes from the derivation of so basically how we derive it is by so we look at the correlation function inside a finite volume, and which is a continuum correlation function, and finite volume dependent part is what is well known, and that comes from this known function F inverse, and then this M is the scatter.
So is it calculated from the lattice? You
Uh,
calculate F inverse and then compute the determinant. I don't know where this
uh,
F inverse
so
F
F
inverse
inverse
is coming from.
it just comes from phenomena. It just comes from like lattice phenomenology. It's a very it doesn't depend on the I mean unless it just suppose if you have a periodic lattice, like the F inverse is just some zeta functions. It's like some combination of zeta functions that is just well known. It just comes from the it just comes from the
You
periodic.
say it is well known, but then you should be able to describe how you get it, no?
Huh,
It's not well known it's well known maybe in the lattice
mhm.
community, but not well known
Uh,
outside.
Yeah, so how you get it is by you calculate these, for example, these using Bethe salpeter kernels. So what you do is you calculate. So if you have like a scattering happening, and then so what you do is things that things that don't go on shell. The actually it doesn't act. Only the intermediate particles that go on shell, they sample the volume, because if you're on shell, that means like you have like long range, you can move. So what you do is you calculate the difference between the for example, for a 2-point function, you calculate the difference between the continuum values. You don't know the value, you know the difference precisely. So what you do is you calculate the value in the continuum as well as you calculate the value in the lattice, and the difference between them comes as a function of the lattice volume, and that is how you get this function.
Okay. Okay. I have other questions also. You also talked about using higher pion masses.
Mm.
Uh, I am a bit confused by that. We know that. What do you mean by using higher pion? How high a pion mass do you use?
So in our case, what we've used is like pretty high, like 0.5 GeV to 3
So
GeV.
500 to 500 MeV to 300 MeV. But we know that pion is 139 MeV, right?
Right.
So um, what does it mean to make a prediction based on a pion which is 500 MeV? Whereas the real world pion, what does it mean to make a prediction about the real world, where in the real world the pion is about 140 MeV, but you are using a pion mass of
Mhm.
between 300 and 500 MeV?
Right. So this is obviously like one of the limitations of our calculations, whereas we started off with like a very high pion mass, but
In
then
fact, if I understand your this thing correctly, do some people even take the pion mass to be 1 GeV?
uh yeah, so here in our calculation we have taken the pion mass to be 1 GeV as well.
You have taken it to be 1
Yeah,
GeV.
so it goes
Okay.
0.5
All
to
the way from 300
yeah.
MeV to 1 GeV.
Mm-hmm. So
So if the pion is so heavy,
mm-hmm.
anything between 2.5 to 5, 7 times heavy
Mm-hmm.
compared to the real pion.
Mm-hmm.
What is the meaning of the statement that you are making a real world prediction?
So what we are hoping is that when we do the the chiral extrapolation, we are taking care of. So this is we perform a chiral extrapolation, and we are hoping that with this chiral extrapolation, we are taking care of the fact that the pion mass is not the physical pion values, but obviously this is a limitation. So we would in future calculations we would like to have much lower pion masses. Close to physical is very hard just because of the computational limitations. Because if the pion mass is very low, then we need enormous, very huge lattices to do the calculation, so that the volume effects are not too large.
Okay. You also use this phrase chiral continuum extrapolation. What do you mean by that?
By that, what I mean is I have different lattice spacings. So we do a combined. So we can either do a separate extrapolation for the continuum where we take the lattice spacing to 0, and then we can do a chiral extrapolation, which I've shown here, and like both together, or we can also do it both together, it is just called a chiral continuum extrapolation. We're doing the chiral extrapolation and the continuum extrapolation in the same fit.
No, I mean, I don't mean as a technical, what you do technically. I just don't understand what you're doing in terms of physics. Why chiral? And what do you mean by,
Uh,
are you saying chiral in the sense of going to zero mass?
yeah, going to the physical,
Or
yeah,
going to low mass?
going to lower pion masses.
Okay.
Yeah.
So you work with pions of mass 300 MeV all the way till 1 GeV, and then you try to extrapolate down to 139 MeV
Using models inspired by chiral field theory.
using models inspired by. So that is an input outside of lattice gauge theory. Is that right?
Yes.
I see. Okay. But within, but if I were to go back to your result, which was towards the end, here were you able to successfully implement the chiral continuum limit and work with a pion mass of 139 or 140 MeV, or here the pion mass was still fairly high?
So here, what I have is a physical value that we've extrapolated. So we use all the different pion masses, and then we extrapolate using some chiral models. And this is the value that I've quoted from this extrapolation.
So what is the pion mass that you are using finally?
So the extrapolation, we just use the physical pion mass. So 139 MeV, we extrapolated to that value. But the model, we use a chiral inspired model to do this extrapolation.
Okay. Okay, and just one last question. You mentioned that you want to do radiative corrections, but for that, won't you need to couple electromagnetism?
Yes.
So, how do you plan to do that?
So this is something this would be just with 3-point functions. So then you have these so similar to what I have in your 2-point functions. So what I would just have is in first order of alpha QED, I'll just have a electromagnetic current, and I'll calculate 3-point functions on the lattice, and then I can calculate the couplings.
I see. Okay. Okay. Yeah. I have no further questions.
Any other questions? Okay, if not, let's thank Archana for the very nice talk. Thank you, Archana, and thank you all. Thanks, everyone. Seminar is over now.